what if we have output but we don't know the multiplier or the increment or the modulus? It was modern at some point to use secret LCGs for cryptography purposes, but that's of course not a very good idea, and we'll see why. Well, finding the increment is actually rather easy. Well, we multiply the previous state by A, subtract it, and we have B. Since S1 is nothing else than A times S0 plus B. But in order to calculate B, we actually need A and M. So this is an implementation in Python that does exactly that. So we also need the multiplier, but we need to find it without access to the increment, because we need the multiplier in order to recover the increment. For that we need 3 outputs to recover the multiplier. We just observed that S2 minus S1 is, as we've seen in the previous slide, essentially A times S1 minus A times S0, the previous states, and that is the same as this here. So in order to find A, we might as well just take this number divided by the output 2 minus output 1 divided by output 1 minus output 0. Or here I will take that just so it's more obvious that I'm talking about the multiplicative inverse regarding the modulus. And then we have found A, just given 3 outputs. There's a Python function implementing exactly that. Just taking those 2 states, subtracting them, dividing them by the subtraction of those 2 states, taking modulus, and we have found A, or the multiplier. Okay, so now we can recover the multiplier and the increment, A and B, but we still need to find the modulus, and that's a bit more complicated. So we want to find the modulus without having to find A and B. Key observation here is that if I subtract an output from the previous output multiplied by A and increment that by B, we'll get 0 obviously, because this is essentially congruent, or not essentially, this is congruent to S1, right? Because if we calculate that mod M, we get S1. So if you subtract them from each other, we get 0. It's actually congruent to 0. This means, as we've seen in the modular arithmetic video, that these 2 numbers differ by a multiple of the modulus. The multiple here is K0. So the idea is to collect enough of those multiples of the modulus, and then we can use the greatest common divisor of our collection to find the modulus. But since we don't know the multiplier or the increment by this point, we're gonna use a trick. Namely, we're gonna set K0, okay, given two outputs. And, well, K1 is this output, and the successor is 2. Well, this we can also just write as, since this is going to be 0 modulus m, we can also just write it as the multiple here, this multiple of the modulus. So K1 is essentially K0 times the modulus. We spin this further until K2, and now we can do this neat trick. Multiply K2 and K0, and then subtract K1 squared. As you can see, this will also be congruent to 0 mod m, so this number here only uses outputs, not the multiplier, not the increment, just outputs, and generates a number that's 0. So a number, this number is a multiple of the modulus, right? Because that is 0 mod m. Everything 0 mod m is a multiple of m, because the remainder, by dividing it by m, is 0. So with the greatest common divisor, which is an efficient operation, we can always use the GCD. Once we have collected enough numbers like this, we can most likely recover m. There's a bit longer function in Python implemented, and it recovers the modulus just by inputs. So now we have a method of just by inputs recovering the modulus, then recovering the multiplier, and then recovering the increment. So no, it's not safe to keep your LCG parameters secret.